Okay, what we're going to do now then is repeat what we did in the previous section, but we're going to prove some more things and be a bit more careful about how we do things. So as before, let's assume that we've got data vectors x1 to xn and that these are all in Rp, they're all of length p. Let's suppose that x bar is the sample mean. Okay, and I'm not going to assume we're row-centered anything now, so the sample mean might be non-zero. And let's let S, which we be the sample variance, which we compute as X transposed H X. So this is a sample covariance. Now let's suppose that S has spectral decomposition, that is V lambda V transposed, which we can write as the sum from J equals 1 to P of lambda J Vj Vj transpose, where the Vj's are the eigenvectors, lambda J's are the eigenvalues. So we've got S Vj equals lambda J Vj. Okay. And capital lambda is the diagonal matrix, lambda 1 down to lambda P. 0 is off diagonal. So principal components analysis then is defined sequentially. So the jth principal component is the solution to the following optimization problem. So we want to maximize U transposed S U with respect to U, but we're going to say that U has to have length 1. And we're going to maximize this subject to U being orthogonal to all the previous principal components found. Okay. So we're going to require that Vk transpose U equals 0 for k equals 1 up to j minus 1. Okay. So when j is 1, there's no orthogonality constraint here. Okay. There's just we just maximize this variance term subject to the vector being of length 1. But when j is bigger than 1, we have these additional constraints. So for j equals 2, we maximize this variance term where u has to be length 1, but it also has to be orthogonal to whatever the first solution was. Well, I should say where Vk is the solution to the kth optimization problem. So the proposition we want to prove is that for the jth problem, the solution is that the maximum of U transposed SU is lambda J, the jth eigenvalue, and it's achieved at U equal to Vj, the jth eigenvector. Okay. So this is exactly what we saw in the previous section. We're just going to be a bit more careful about the proof here and prove it a bit more cleanly. So this is a constrained optimization problem. Okay, so we're going to try and prove we're going to try and solve this using the method of Lagrange multipliers. So first of all, for j equals 1, we want to maximize U transposed SU subject to U transposed U equals 1. Okay. So the method of Lagrange multipliers, hopefully you've all seen this before, is we set up our objective, so I'm going to call that L, which is the thing we really want to optimize, U transposed SU here, plus lambda times our constraint. So our constraint here is 1 minus u transpose u. Okay, so lambda is just a general variable here. So we want to differentiate this with respect to u and with respect to lambda. So if we differentiate with respect to lambda, first of all, we get our constraint back, 1 minus u transpose u. Okay, and we're going to set these derivatives equal to 0 in order to solve the optimization problem. Okay, so let's differentiate with respect to u. Well, here we're going to get 2 su minus lambda u. So we're going to set this again equal to 0 at the optima. Okay, because the derivatives are 0 at the maximum. Yeah. So this gives us the first equation. Well, I missed the 2 here, didn't I? Right. So the first equation is going to give us su equal to lambda u, and the second equation just gives us back our constraint, u transpose u equals to 1. Well, what's this first equation, su equals lambda u? Well, that's just saying u is an eigenvector, or let's say u must be an eigenvector of S and lambda an eigenvalue. So if we substitute this back into our objective, so we then have that u transposed SU, well, if u is an eigenvector with eigenvalue lambda, this is just u transposed lambda u. Well, let's bring the lambda out the front. That's lambda u transpose u, but u transpose u is 1, so this is just lambda. So we haven't said which eigenvector to pick yet, but this objective tells us we want to maximize this. And so the way we maximize it is by picking the largest eigenvalue. Okay? So thus pick u equal to v1, okay? The eigenvector corresponding to the largest eigenvalue, lambda 1. Okay, so that has proved the part of the statement for the j equals 1. So now let's assume the proposition is true for k equals 1 up to j minus 1. So the jth optimization problem was maximize u transposed SU subject to u transposed u equals 1 and v k transposed u equals 0 for k equals 1 to j minus 1. So we need to pick the direction u that maximizes the variance conditional upon the direction having the vector being of length 1 and the direction being orthogonal to the previous direction that we've already found. So let's do what we did before. Let's set up our Lagrangian. So that's going to be the objective that we're really interested in, which is u transposed SU, as before, plus, again, some variable lambda times 1 minus u transposed u, plus this time we've got j minus 1 other constraints, so we need to include them as well. So we've got the sum from k equals 1 to j minus 1. Let's call these Lagrangian multipliers mu k. Okay, and the constraint is u transposed v k. Okay, because we want these to be equal 0. So again, differentiating the L by du, equals 2SU minus 2 lambda U plus mu k v k sum. And as before, we're going to set this derivative equal to 0. Obviously here, if we differentiate with respect to lambda or with respect to any of the mu k's, we're going to get back our constraints. Okay, so I won't bother writing that down. But let's take this expression we've just computed and left multiply by VL. Okay, so that's going to give us 2 VL S as VL transposed. Let's say multiply on the left by VL transposed. So VL transposed S U minus 2 lambda VL transposed U plus the sum of mu k VL transposed VK equals 0. Let's just assume that L here is less than or equal to J minus 1. Well, the first thing to note here is that VL is one of our eigenvectors of S. Okay, so S VL is lambda L VL. So S is symmetric, so we have that VL transposed S is lambda L VL transposed. So this is going to reduce to 2 lambda L VL transposed U minus 2 lambda, well, VL transposed U has got to be 0, yeah, by our constraint. So this is times 0, so let's just ignore that term. Then this term, well, VL transposed VK is 0 if L doesn't equal K, and it's 1 when L equals K. So this just gives us mu K equals 0. Now, similarly, we can go back here and say that VL transposed U has got to be 0 by our constraints. Our constraint is that U is orthogonal to the previous solutions found. So what we end up with is that the mu K must equal 0. So going back to our expression here, we are left with, this here should have read mu L, shouldn't it? Okay, because when we multiply by VL here, we pick out the element of this sum, mu L. Okay. So when we go back to our expression here then, we are left with, we cancel the 2's, S U minus lambda U equals 0, or in other words, SU equals lambda U. So in other words, we've again found that U is an eigenvector of S. So all that remains to do is to show which eigenvector it is. We know that, as before, U transposed SU must be one of the eigenvalues, but U has to be orthogonal to VK for K equal to 1 up to J minus 1. So the largest eigenvalue we can choose is lambda J. Okay. So if we choose U equal to Vj, okay, we maximize U transposed SU. Okay. So that proves the result. So to summarize, we find that the principal components are the eigenvectors of the covariance matrix. ordered by their eigenvalues. So the first principal component is the eigenvector corresponding to the largest eigenvalue. The second principal component corresponds to the second largest eigenvalue, and so on.